Hello and welcome to the channel. On this channel, I will be teaching Comsol multi-physics basic tutorials for beginners, and we'll start with basic terminology related to the software and similar softwares, which is modeling and simulation, modeling and its types, and simulation and its various types. So then, after that, we will move on to the basic introduction to Comsol multi-physics software, uh, and we'll start with the user interface. What are the various options, how we can use the software, uh, what are its various stages, various steps. We'll cover all that, but before that, modeling and simulation is very important to be understood beforehand. So starting with Comsol, uh, basic terminology, that's modeling. And what is modeling and what are various types of modeling? So we'll start with modeling. Modeling is the process of creating a simplified version of a real system to understand, analyze, or predict how it behaves. Now, what does it mean? It means, for example, suppose a river is flowing and we want to construct a bridge over this river. Now, we do not directly go and start building the bridge because we need to make it clear that how big the bridge has to be, how strong the bridge has to be, how much load the bridge has to carry. For example, there's a full of transport. What kind of transport can move onto that bridge? What can be the possible what can be the heaviest possible loaded truck that can move on that bridge. So accordingly, we have to make that bridge that strong, that big in size. We have to use the thicker element, a stronger material, and all that. So we do not directly go and build the bridge, then make a heaviest truck move over it and test it that way. No, that's risky. We do not do that. So because that is consuming a lot of money, that's consuming a lot of time. So what we do is we take the help of computer and we make a geometry of that bridge. So we will be having the size of the river, then we know what size of the bridge should be, how big it should be, whether it's a single lane bridge or a simultaneously two or three vehicles should pass through the bridge, and all that. We know all that in hand, so we know the size of the bridge. Then after knowing the size, we will be having what we'll be having in hand is what maximum load that bridge can have on it. So accordingly, we have size, we have the maximum load that it has to bear. So accordingly, we can make that bridge using a computer first, like for example, we use a computer and then we use geometry, we use like modeling, we use like CAD softwares like SolidWorks, AutoCAD, Creo, Catia. So all these softwares are the CAD softwares in which we can make the solid geometry. So using these softwares, we can make the geometry of this bridge. And when we made the geometry of that bridge using any CAD package, so this is not now the real world system, or in our case the bridge, but it is the something that we have made on the computer using computer program to act like this real world system, to act like that bridge. This process is known as modeling. So creating a simplified version of the real system. So this will be the simplified version of the real system. It will not be having all those members on it. It will be a simplest structure that we want to study. Now, for what? To understand how this bridge will work and predict when we apply using the computer program, when we apply this maximum weight on it, and we will be seeing that where are the points where the stress will be concentrated the most. So because those are the points, those are the critical points in the design of that bridge. So we will make sure that at those locations, at those places of this bridge, the strength of the material, high strength material is used. We'll make sure that the thicker materials are used at that locations, so that that critical stress locations are dealt with. So making the simplest model of this real system, we call it modeling. Then when we model the actual system, so basically if we see, the modeling is basically a setup. So what we are converting a real world system into a simplified version using computer or any other means. So this soon as we are modeling the bridge. So once the bridge is modeled, after that what is done, it is tested. Like if we wanted to build the actual bridge, then we have to test it. We have to place a load on it, the maximum possible load that can be placed on it. So based on that, we have to test it. What are the points where it the citrus concentrators and all that. So in the similar manner, now since we have modeled the bridge, we have to test this model. Now testing that model is known as simulation. So basically, modeling is the setup and simulation is the test that we will do on it using computer programs. Using the computer program, we'll apply this same maximum amount of weight on it and check the critical points. And based on those critical points, we will design the actual bridge, and we will know these are some critical locations, and at that locations we have two options to increase the strength of the bridge. Either we have to use the stronger material, or if we cannot change the material, we will increase the thickness of the material. We'll make sure that the material at those locations is thicker than at other places where stress is not that much localized. So this is in short, this is modeling and simulation. Now, types of modeling. Now there are some types of modeling. For example, physical models. For example, physical models. Uh, Physical models are reduced scale models. So what does it mean that a model is a reduced scale model? First of all, the model I explained here is basically a computational or computer based model. What's a physical model? So for example, a company wants to build a new racing car, say. Now, since it's a racing car, it has to go as fast as possible. So for that, one of the constraint to this condition is that the air drag has to be as low as possible. So what will the company do is, it will not directly go and build a car, then drive it on a road and check how much air drag applies on it. Then it will see now the air drag is high, so after that it will change the design again and throw over that initial car. No, it doesn't work like that. That costs a lot of money and time. So what they do is, they make a model out of it. They make a simplified model and a reduced scale model. So when they make a model out of it, that is not a real car, that is just a reduced scale. Suppose a small, and what they're interested in is the shape of that vehicle, because they are studying the air drag, so shape really matters. So they will make a small sized model of the same material or whatever, same weight. For example, if it has weight suppose like 100 kgs, then if it is reduced to one half, so its weight will be like 50 kgs and all that. The size will be reduced to half, everything will be reduced to half. So this is known as a reduced scale model. Then since it is a model, it is not a real car, so they cannot drive it on a road. So what they do is they put this model inside something called a wind tunnel. They'll put it inside a wind tunnel, that when that wind tunnel is started, the fan moves, it blows the air. Now we can control the speed of the blower there, and accordingly we can have the same speed of air at which the car actually will move at the faster, at it is say maximum speed. So if the car has a maximum speed of something, say like 200 kilometers per hour, so we will make the air blow at the same speed, 200 meters per second, because these are two cases. One, air outside is almost still, and car is moving at say 100 kilometers per hour. It is same as the car is still. It is same as that car is still stationary and air is moving at the same speed, because motion is relative. So this will have same effect. So we keep that model at rest inside the wind tunnel and make air go over it at the same speed at which we want to test. This will give the similar result, and based on this we'll see how much drag is applying on the car. So accordingly, if it is high, we will change the shape of the car, we will change the shape of the, we will try to make it more streamlined. We'll try to make it more streamlined as possible, because more streamlined it is, the flow over it will be more laminar type and the air drag will be lesser. So we will make it more and more streamlined. Then we make another model, because making these models are very simple and very cheap. We make another shape of this model, place it in the wind tunnel, then test it, and we will repeat this process until we are satisfied with the shape of the car, based on the least possible drag from the air. So these are called physical models, which are where we use reduced scale models, small sized models. Then once the drag here suppose is obtained, suppose we get the drag force of say suppose 10 newtons, and since this is a small reduced scale model, how much drag we will calculate from this for this actual system. So that will be, for that we will be applying the scaling laws. Suppose if the scaling law says if the model is reduced to half, then whatever air drag will come, that has to be doubled. So if the scaling law works like this, then we will say that that actual model, that actual system will be having the air drag of around double, that is the 20 newtons. So this is how important, how significant this modeling process is in science and engineering. Then there are mathematical models. In mathematical models, we have an actual system. And we convert it into mathematical equations. We solve those equations, that means we have solved that system. That's another way. That's called, that type of modeling is called mathematical modeling. For example, we have an object of some mass, and it is acted upon by some force, say F, and we want to see how much the acceleration the body will gain using this force. So this is our actual system. So we do not need to have a mass of a body of that mass, and we do not need to have a physical system that will apply a force on that mass, and then we do not need to have setups, apparatuses they attach it to it that will measure the acceleration. No, that will be time consuming and that will be costly. So what we'll do is we use directly the equation F is equal to ma. So this equation is the governing equation of this system for studying its mechanics. So this will be the governing equation. So this physical system we have converted into a mathematical equation. So whatever this mathematical equation gives will be the same result, depending upon how accurate the model is, will be giving the same result as is given by those experiments which I explained. So we call this is the mathematical model of this physical system. So what we'll do is we will solve this equation F equals ma, or acceleration from this will be F divided by m, and we'll solve this. So that's also testing a system, studying a system, predicting its behavior, what its acceleration will be when this amount of force applied on it. So this type of modeling is known as mathematical modeling. uh, Another example for this mathematical modeling is, suppose we want to study heat transfer through a wall. So this is our wall. Say this is our wall, and we want to study how heat flows through this wall. So one way is you studying the physical system in itself. We have to build the wall, we have to increase the temperature on this side to whatever the temperature is in the real system, say 100 degrees Celsius. Then on the other hand, on the other side of the wall, we have to keep the temperature that is the environmental temperature, say 20 degrees Celsius. Then we have to use the sensors, the measuring devices, which will measure the temperature at each point inside the wall and study that behavior. That will consume a lot of money, a lot of time, etc. So what we do is we convert this actual model into a mathematical model. That is, we use the Fourier's law of heat conduction, that this heat transfer rate through this will be K, considering one dimension, K, then this area A, then temperature difference between inside outside, and divided by this thickness. So when we solve this equation, this is studying same practical system. So this gets very simplified. No need of getting materials, sensors, measuring devices. Just we solve this equation, mathematical equation, and that is studying that model. That is studying that actual system using this mathematical model. Then we have numerical models or computational model. A numerical model or computational model is the one that I started with. That is, we use computers, we build the actual system, then we apply forces or temperature differences on that actual system, and computer tells us based on the equations that we have yeah, we have programmed in that software that we have programmed, and based on it solves those equations, solves for all the independent variables that we put, and gives the value of the dependent variable, like the temperature distribution through the wall, stress and strains at different critical points inside the bridge, all that. When we use computer to make those simplified models, we called it numerical or computational modeling. Then there is graphical model, which is like block diagrams that we use in control systems, or circuit diagrams that we use in electrical or electronics engineering to solve a problem in the simplified version before actually using the actual wires and the circuit boards. So modeling is basically a setup. The next we have is simulation. So as I said, modeling is converting a physical system into a simplified version using these different methods. We call that modeling. Then after the modeling, we have to test the model. So the testing the model that we do in actual sense, like we go and build the bridge, then we test the bridge. So building the bridge using different methods, simplified versions, we call it modeling. Then we actually test the bridge. So for that testing, we have a simplified version of testing using computers and all that. It's called a simulation. So simulation is like creating a virtual experiment on a computer. Instead of building something real to test it, we model it digitally to see how it would behave in the real world. Benefits of the simulation is it saves time. It obviously saves money, that I showed how. For example, there are some tests which are difficult to do beforehand, which are risky to do beforehand. So in order to actually do those tests, we make models and we simulate them using computers or any other means. And when we are okay with the model that it would work fine, all that, and then we will proceed with the actual system, then we build construct the actual system. Now there are some types of simulation. For example, structural simulation. Structural simulation means when we actually artificially test the bridges, buildings, etc. For example, test how things like buildings or machines bend or break. So we make a bridge model using a computer, then we apply various types of loads on it and see what are the critical points where it has possibility of breaking or bending. We do all that. This is called a structural simulation, and for structural simulation we have softwares like ANSYS, or we have SolidWorks simulation as well. SolidWorks is we know it is a CAD package, but it has simulation features as well. Then fluid flow simulation. Here, in this simulation, we show how gases and liquids move before actually making the liquids and gases move. What we will do is we use computer softwares, and we actually we model a system, and then we make airflow over it using this program. For example, we have ANSYS Fluent, we have Comsol. Then there is another type of simulation is called heat transfer simulation, in which we study heat transfer problems using computer programs. Like I explained the case of heat transfer through a wall. Suppose we have heat transfer modules in Comsol, in ANSYS workbench that are used. Similarly, we have control system simulation, where model is how machines behave over time using feedback. Like for that, we have simulation software like MATLAB, Simulink. Then circuit simulation, where we use softwares to model electrical circuits without real wires, to first test them, how much heat will be produced, say what will be the how much currents will flow, how much heat will be produced, how sophisticated the cooling system should be, and all that. So for that, we have software like Tinkercad circuits or Multisim, etc. So this is the basics of modeling and simulation related to Comsol, multiphysics, and similar softwares. So in this class, we studied what is modeling and what are its a few types, and what is simulation and what are its various types. And in a nutshell, we found out that modeling is basically a setup, making a simplified setup of actual system, and simulation means testing that simplified version in a computer before actually testing it in the real world. Based on these modeling and simulation, we get results, and based on those results we start building the actual system. Thank you.